All right, here we have our transfer function here. This was developed from a circuit, and right now we're going to create a Bode plot, a straight line approximation. The point of this is not to be 100% accurate, but so that we have the idea of looking at this transfer function and be able to approximate what it looks like without actually calculating it. So from here we have to approach this slightly different, since the denominator here can't be factored nicely. It'll factor into imaginary roots. We have to use a different method where we can take the constant here, and that will turn into, that is Wn squared equals 25, which makes Wn equal to the square root of 25 equal to 5. From there, that gives us our break, and then that will allow us to come up with our ranges. So for s less than 5, and for s greater than 5. For s less than 5, we will take the transfer function this is, in the numerator, this is 25, not 2s, and this is 2s, not 25. Also, this is 25. Here, we, for s less than 5, we will cross out s squared plus 2s, leaving us 25 over 25. That's 1. So then, just for the procedure, 20 log, turning this into dB of 1 is equal to 0 dB. So any point where s is less than 5 is 0 dB. And then for s greater than 5, squared plus 2s, 25. We have to figure out what to cancel out here. So s greater than 5, we will cancel out this portion, leaving us with 25 over s squared. That will transform into 20 log 25 minus, because of the division here, 20 log s squared. That turns into just log properties of log. The squared pulls out in front and becomes a 40 out here, just becomes multiplied. So that's 40s, or 40 log s. So then let me clean this up a little bit and proceed to the next step. At this point, we already know that anything less than 5 is a constant at 0 dB. Now we just need to figure out for s greater than 5, where we will take this and do 20 log 25 minus 40 log s. So since we only need s greater than 5, we don't need to, we can just pick anything at any point, and the 2 points that I happen to pick were 10 and 100. Just because these are easy to approximate, and then when we plug these in into this equation, we will evaluate them at negative 12 dB and negative 52 dB. And it's important to notice that when you actually calculate these, they will come out to be negative 12, negative 12 point, I think, 04 dB, some decimal, and negative 52.04 dB, some small decimal. Those can be ignored because we're just approximating this. Plotting 0.04 on a graph is not necessarily an easy thing, so we just avoid that by just, making it simple. Then from there, we have 2 points, which we can get a line from. We know at 10, we'll be at negative 12, so 10, negative 12, and 100, negative 52. And that will give us the straight line here. We can just extend that all the way up. And then we know that at less than, or we know that there's a constant line at 0, s less than 5. So we just draw that across. It's a straight line approximation, so like these overlapping bits can just be canceled out. Those, and this would be the break. An important thing to note is typically this would be the end of the approximation, but if we go back over here with this form not being able to be factored evenly, we have to use zeta to find out if there's peaking or not. And by doing that, we have this scale here that will help us determine if there's peaking or no peaking within this graph. So how we do that is the general form is s squared plus, I'm just going to call it x zeta ws plus wn squared. This is the same form as up here, and from that we can find what zeta is. We do that by taking the coefficient zeta, and then from here wn is 5, and we equal that to this coefficient, which is 2. So then zeta equals 2 over 10, 0.2, and from there, that is zeta. If we look back at the scale up here, we find out that it is less than, that is less than 0.5, so there is peaking. And to find out where that peaking is, we use 20 log 1 over 2 zeta. My zetas come out different every time I draw them. So then we do 20 log 1 over 2 times 0.2. And that gives us 7.96 dB. And then from there we know that there is peaking at 7.96. Let's just call it 8. So then from here we know there is peaking at this point, going upward to about 8. So right here there is peaking. Let's get rid of these extension lines here. So about 8. So there will be peaking at this point. The actual graph is a little bit curved, comes up to this point, and then falls back down. And that is how you determine if there's peaking in your Bode plot.